All right, so let's do one last example. This one's I chose kind of an awkward looking transformer for this particular case. Basically, again, I just got a review of all the stuff here. So general load with impedance, voltage, current. I may ask you, you'll see this like on the practice exam in the past, like I've done stuff like this where I say, okay, well, you tell me what the time domain waveform looks like, or give me an expression for what it would actually be, which would mean that whatever your currents or your voltages are, you would have to do what to figure out the right answer? Multiply by square root of 2, right? That type of thing. I probably won't ask anything probably about the instantaneous power. I talked about it. It is important, but it's not, honestly, most people don't think about it too often. All right, so I don't ask you a whole lot of questions about it. Key thing for us, in general with our loads, right? Impedances in the first quadrant are inductive. Impedances in the fourth quadrant are capacitive. Do I have impedances in the third or the second? Yeah, I mean, typically no, because that would mean a negative resistance if I was over here, right? I would have to have some kind of active device that was generating power to be able to do that. Okay, that's outside of 2112. Okay. All right. So basically, we deal with the impedance angle is what determines that, right? All right. So basically, we said an inductive load is said to be lagging because the current lags the voltage. Capacitive load is said to be leading because I leads the voltage. What does that mean? Basically, what we said is that from Ohm's law, we have V equals I times Z. So basically, the angle of the voltage equals the angle of the current plus the angle of the impedance, right? So the angle of I is always the angle of the voltage minus the angle of the impedance. All right, so if I have an inductive load, what's the angle of the impedance? Positive or negative? Positive. That's why I get lagging, because I have to go backwards. I subtract. I have to go backwards from the voltage. If it's leading, I would have a negative impedance. That's a capacitive device, a negative impedance. So I would end up adding to the voltage angle. As I say, the current leads the voltage. Okay. So all those results are important for us. Then we've got a summary of everything. All right. So here's the problem that we're going to try to address today. And I don't know why I defined that current right there. All right. Now, I'm going to go through the set of questions I'm going to ask. I'm going to call this guy here V sub S. Sort of an awkward looking circuit. In a real distribution system, you wouldn't have a circuit like this. This guy is 0.1 ohms. And this guy here is negative J times 0.1. You wouldn't have a circuit with an RC like that probably, but I wanted to make it trickier. So there you have it. Okay. All right. So load A, which is on the primary side of this transformer, is 10 kilowatts, 0.87 lagging. Load B is 10, what's that? kVA. All right, 10 kVA with 0.9 leading. Okay. All right, so we'll go through those. So what do I want to know? I want to get the transformer relationships. What I call the power triangle. Power triangle is basically the S vector, and I want to know its components, right? I want to know what the P and the Q are. A lot of times people call that power triangle. And then I1, I2, which are the transformer currents, V1, IA, and V sub S. All right, so here's our circuit. And I don't know why I put that errant thing up there. Let's pretend that's not there. Okay, all right. So how do I do this? Let's do that first part, which is the transformer relationships. And I guess I didn't write it on here either. V2, as it's defined right there, V2 is 480 volts with 0 angle. Okay, so just 480 volts. Okay. All right, so where do I start for the transformer relationship? And I didn't write a lot of stuff. 8-to-1 is the transformer turns ratio. So 8 turns. That doesn't mean 8 turns on the primary. That means that 8 times the turns on the primary. All right. You wouldn't have a one-turn transformer typically.
I would say start at OD and determine the real power and rectifier.
Yeah, and that's it. Yeah, exactly. We will want to do, we'll start there when we start doing all the calculations for sure. If I want to get the transformer relationships, just, okay, what's the V1, V2, I1, I2? Where would I start with that? You're totally right. That's where we're going to start with the rest of the problem. Well, so just the transformer. I want to figure out the ratio of the voltages, the ratio of the currents on the transformer. So where do I start with that? I want to get the V1, V2 relationship. Based on the way I drew this, what's the V1, V2 relationship? So we always said it's the magnitude of V1 over the turns. So V1 over N1 equals V2 over N2 in terms of magnitudes. I mean, it's going to be negative here, right? So what do I have on the primary side? I have the plus sign at the dot. On the secondary side, I have the negative sign at the dot. That's when I get a situation where I say V1 over N1, so V1 over 8 equals negative V2 over 1. All right, or simply V2 equals, well, V1 equals negative 8 times V1. All right. Again, the way I look at this, the side, 8 times V2. Sorry. The side with more turns always has more voltage. So I've increased the voltage by a factor of 8 to think about what the primary side voltage is. Okay. So that means it would be 480 times 8, at least in terms of its magnitude. The fact that it's a minus sign means how many degrees of shift do I have? 180, right? That's 180 degree shift. Okay. So now how do I get the current relationship? Do the power part. Yeah, that's right. So what's the power on the primary side? Based on the way I wrote this. Well, yeah, V1 times I1. V1 times I1. What about on the secondary side? Positive, because I1's going into the plus sign. And then what do I have on the secondary side? It's negative V2 I2, yeah. Why negative? Yeah, so the arrow would be entering the negative terminal or leaving the positive. So I say it's that. Okay. All right. So I end up with that result there. Now, what do I do? I end up plugging in my results here. So I say V1 equals negative 8 V2. So I end up with negative 8 V2 here. I1 minus V2 times I2 equal to 0. If I carry all that through, I'm going to end up that I1 is equal to negative I2 over 8. Like that. Okay. So both of our results have a negative sign. Now, nobody would ever do what I just did and define the voltages like this, right? Most likely they would have put the plus sign at the dot, right? I'm just trying to test your understanding of it in the power context. So there's places where you would do this and do, but not commonly in the power type of problem like this. I'm just trying to test your knowledge by setting up a problem like this. Yes.
So, are we always gonna like solve for like V1 and I1, like just on one side of the equation, or can we do like V1 and then solve for I2? That doesn't really matter.
Yeah, I mean, it doesn't matter. I mean, somehow you got to do the voltages first to get some relationship, because that just comes from knowing the turns ratio. And then in your power equation, you just got to substitute in one way or the other, either for V1 or for V2. Right, the V2s cancel here, and then you're left with some relationship between I1 and I2. Right, I mean, those definitely cancel. because, and they would factor out that a V2 times something equals 0. V2 is not equal to 0. So we know that that's cancel out of that equation. Always get something like that. I could solve, I plugged in for V1, I could have plugged in for V2. That's, doesn't matter. Either way, the voltages go away. All right. So now we're going to do the next thing, which was the relationships. So the suggestion was to start with load B, and that's what we'll do. So for load B, I was told 10 kVA with 0.9 leading. Okay, so leading, what type of load do we have? Capacitive load. What's that tell me about the angle? The angle of that is going to be negative. It's going to be in the fourth quadrant. Okay. All right. So what else? What have I been told by being told that it was 10 kVA? I'm told the magnitude of S. All right, not S. It's tricky. It's the magnitude of S. Okay. So I was told that the magnitude of S is 10 kVA. So if I drew the vector, all right, here's what I know is that this here is SB magnitude. And I know that, all right, the other sides of the triangle there, how do I label those? Which one's P and which one's Q? It's real. Yeah, P is real. And Q is imaginary. And I made it negative because this is a load that is lagging, or sorry, leading. This is a load that's leading, and it has a negative impedance angle because remember, SB, the vector there, the complex power vector, is got a magnitude apparently of 10 kVA and an angle that is the same as what angle? Power factor angle or the impedance angle, right? It's the same as whatever the impedance. So whatever Z sub B is, right? Whatever that load is over there, it would have that angle. Okay. And we know that that's negative because we said it's a leading load. Okay. All right. So, and that's the angle that I would define here. All right. So how do I do this? How do I get P and Q? Trig. All right. It's just a simple trig problem. Okay. So help me out. How would I get P sub B? How would I get P sub B? Yep, and I know that the cosine is already put, so in other words, I've been told that I got to be careful, right? The cosine of 0.9 is equal to the cosine of phi ZB. Okay, and I know that the power, if it's the real part of this vector, right? The power is equal to the magnitude of S times the cosine of phi ZB, like that. So what would it be? Without using your calculator. Yeah, magnitude of S times 0.9. So this guy's going to be 9 what? Kilowatts. 9 kW. Okay. I should be making one little peeve of mine. Is this should be I won't take any points off because the P of mine, the K should be little and the W should be big. They shouldn't both be big. All right. With units, we only use capital letters if it's somebody's name. So watts, volt, amp are all somebody's name. All right. K is just kilo. That's nobody's name that I know of. All right. Anyway, this is a P of mine. All right. So how do we do Q? How would I get Q? Pythagorean theorem, or I could do the sine, but I'll do the Pythagorean theorem, which would be the magnitude of S squared minus P squared. Right? I have Q squared equals Q squared plus P squared equals S squared. Right? To do this. Now this is going to give me a positive number, right? But so I'm gonna have to forcibly make it negative, right? So I put a negative sign there because the Q is actually gonna be negative. I have to think about the fact that it's gonna be negative. And what do I end up with if I do that? Did I not write it down? Oh, I did. Negative 4.3589, and give me the units on that. Kilobars, volts, amps, reactive. All right. So now if I wanted to say, okay, well, what is that? So in rectangular form, S, the complex power is 9 kilowatts minus J times 4.3589 kilobars. What would that be in? So I'd say 9 kW minus J times 4.3589 kVars. How would I write that in polar form? What would that be in polar form? What's the magnitude? 10 kVA. With an angle of what? How do I get the angle here? Yeah, I can do the imaginary over the real. It's the same as the impedance angle. So basically, I could use this relationship right here, right? The thing I got to be careful of is cosine is, for an angle that is negative, cosine is going to be positive in the fourth quadrant. So if I do that, the thing I got to be careful of here is I got to say phi sub ZB is equal to not the inverse cosine, but what? The negative inverse cosine of 0.9. In other words, that doesn't come straight out of the math, right? Now, I could also have said it was the tangent, right, of this divided by that. That would work, right? But if I look at the power factor, I know the power factor is 0.9, so I can do the inverse cosine. But I got to be careful. I got to add mentally that minus sign because I know the fact that it's leading tells me that it has to be negative. Because the answer that I get here is what? Is negative 25 degrees. The problem is, what's the cosine of 25 degrees? It's also 0.9, right? So I have to manually put that negative sign in there. Okay. Do you have a question? Okay. All right. All right. That's the tricky part usually. You have to do the thinking on that. All right. Questions on this? Yeah. Which part? Here? This part?
Yeah, so isn't the.
So since I was told here that the apparent power is 10 kVA. Right. That's the length of this side. That's the magnitude of the vector. Right. So basically I know I could also have done the Pythagorean theorem with these numbers and I would have gotten 10 kVA for that. Right. So this works out to be that, and I guess I'll write the negative 25 there. Does that answer your question? Okay. All right. And again, the terms we use for these things: real power, reactive power, apparent power. All right. So now I want to figure out the currents. All right. So I'll worry again. I'll get rid of this. I said V2 was equal to V2 is equal to what? 480. Okay. So let's figure out the current I2. How do I figure out that? How do I figure out that? Well, I could I use Ohm's law? All right, so let's go with that suggestion. I could if I knew the impedance, I guess, on that load. Yeah, which I could figure out the impedance, I guess, because but I'm going to say the simplest way typically is to say S is equal to not VI conjugate. Okay. So well, let me see, I called that SB. Load B is on side 2. The load B has SB. That's equal to V2 times I2 conjugate. And we said previously that this was 10 kVA with an angle of negative 25 degrees. Notice, to get that triangle, that power triangle, I really probably could have just gone to that statement, 10 kVA, negative 25 degrees, pretty quick. I know here's the magnitude, take negative inverse cosine of that, I get to that vector pretty fast. All right, that probably is the fastest way to do it, in my opinion. All right, I'm just taking you through it to make sure you understand it. Okay. All right, so how do I get the angle of the voltage? Or sorry, the angle of the current. How do I get the angle of the current? This is 2 equations, right? Yes. So what are the 2 equations I have here? Magnitude and angle, right? So I say the magnitude of SB equals the magnitude of the voltage times the magnitude of the current. I can use that to solve for the current, right? We know that the magnitude of S is 10 kVA. We know that V2 has a magnitude of 480. That tells me that I2, if I do the math on I2, I end up with I2's magnitude being 20.833 amps. Okay. What's its angle going to be? What's the angle relationship? Yeah, the angle of SB is phi ZB, right? What we've been calling the angle of the impedance for load B. That's equal to the angle of the voltage minus the angle, so I'll say angle of V2 minus the angle of I2. All right. The angle of V2 is 0 in this case. So the angle of I2 works out to be what? 25 degrees, yeah. 25 degrees. So if I think about the relationship I have here, V2 is over here. Where's I2 relative to it? It would be up in the first quadrant here. All right. So I2 would be here. Their magnitudes are pretty different. So again, it's hard to draw them. But this guy is, why do we call him leading? He's more positive, right? He's more positive than, so I go, remember the positive direction is always counterclockwise, right? So going from 0 to 25 degrees, I went more positive, right? So he's leading, all right? That's the way we use that terminology. Basically means that in the time domain, his peak, the current's peak would happen before the voltage's peak. Okay. All right. Questions about that? Yeah.
So
It's so when we say it's a leading or lagging power factor, that's to tell us whether or not the thing is pointing in, whether it's capacitive load or inductive, right? It relates to how the current relates to the voltage, but it really is the thing that tells us if it's capacitive load or inductive load. If it's lagging, it's an inductive load. If it's leading, it's capacitive load. So sometimes people will say it that way. Instead of lagging, they'll say 0.9 inductive. Okay. The reason I'm not saying it 0.9 inductive, people will say it both ways, and I'm making you think more by saying leading or lagging. Right. So that's all. All right. Next thing I do is try to figure out I1. All right. I1 is the current on the primary side. All right. So let's think about current on the primary side. What is that? Well, what do we have to do to figure that out? Current relationship. So let's go back to that. We derived that first. The current relationship is I1 is equal to negative I2 over 8. So it gets smaller. The side with more turns has less current, always. All right, because we're dividing by 8. So I1 is negative I2 divided by 8. So that gives me 2.6042 with an angle of negative 154.1581 degrees. What did the negative sign do? Shifted it 180 degrees. So this is a little bit weird. The fact that it's a negative angle, you don't worry about this so much when I have phasors, right? But what does that mean about the current in this particular case? It's actually the opposite of what I defined. It's actually going the other way. Okay. Or it's actually coming out. Okay. All right. Which is okay because the voltage, if I said, what is V1? The relationship we had for V1 was that it was -8 times V2, which would make this -3840, 8 times 480. What's the magnitude of that? What's the magnitude of this voltage? 3,840. Some of you, half of you probably will say -3,840. Are magnitudes ever negative? No. As a phasor, how do I write this thing? 3840 angle 180 or -180. Okay, you can do either way. All right. That's to say this, so you would never define this like this way. But what this actually tells me is that the voltage should have been written with the opposite polarity and the current should have been written with the opposite polarity so that in my mind, I know the power is going from that source to that load. All right, don't worry yourself with that too much. This is a weird definition that I gave on that transformer. It's just to really practice you for something that you could see. All right, you would never really, you'd never see somebody at Duke defining transformer polarities like that. Okay. All right. You wouldn't know that, but again, as you get more comfortable with that stuff, what I know is happening, just intuitively, you should have some intuition for this. Which direction should power be going? So I think of this power moves through the system, right? It moves from where to where? Well, so you said left to right. Why left to right? Source to load, right? I know that power should be moving source to load. The fact that this has an angle of 180 and the fact that this has a -154 tells me that power is definitely being absorbed into the primary, going to the secondary. All right. If you look at all the problems we've had up until now, where I made more normal definitions, you'll always see that I1 was going into the plus sign. Okay. All right. Anyway, let's do load A. Now, what do we do for load A? Same thing, except in this case, what have I been told? I've been told it's 10 kW with 0.87 lagging. All right, 0.87 is pretty typical for a loaded motor. For what you see, somewhere between 0.85 to 0.9 is pretty typical for a motor when it's loaded. So what is that? What have I been told? By being told 10 kW. I've been told that P, okay? And which quadrant am I drawing this guy in? Which quadrant? It's 0.87 lagging. So lagging tells me that it should be in what quadrant? First quadrant. Tells me it's an inductive load. So it tells me, so right now I know that this has told me that phi sub ZA is greater than 0 degrees. It's between 0 and 90, right? But it's somewhere over here. Okay. And I've been told that the real part of this guy, P, this guy is P sub A equal to 10 kW. And then Q is going up. Okay. How do I label this side of the triangle? You say the magnitude of S. Yep. All right. Apparent power is the magnitude. Complex power is the name for the vector. Okay. All right. So I want to figure out magnitude of S and I want to figure out QA. How do I figure that out? Trigonometry. Yeah. All right. So phi ZA is here. How would I figure out the magnitude of SA? Let's start there. The magnitude of SA. Yep. Magnitude of SA would be P divided by the power factor. All right. The power factor is PA is the cosine of that angle phi ZA. Okay. So two ways of looking at that. One is straight up trigonometry. Think of that thing as a triangle. The other part would be to say the real part of the vector, P sub A, is the magnitude of the cosine of the angle. Right? Two different ways of saying the same thing. All right. If I did that, what would I get? If I did this with the 0.87, this ends up being 10,000. Sorry, no, 10,000 is the real part. This ends up being 11.494. And what units do I give it? kVA. Yeah, good. I said a lot of formulas when you start, it starts looking daunting when you first start it, but I think once you see the mechanics of the problems, it's actually pretty easy. Okay. Hopefully you're seeing that. How would I get the Q? Yeah, trig or whatever, right? So Pythagoras is what I'll say. QA is equal to square root of what? SA squared minus PA squared, right? QA squared plus PA squared equals magnitude of SA squared. Okay. So I go through this whole thing and I end up getting that this is 5.6673. What units? kVar. Okay. So I can say that SA is equal to SA, the vector. What would that be equal to? 10 kW plus J times 5.6673 kVar. If I do it in polar form, what would it be? Let's do it in polar form. 11.494 kVA, yep. And what's the angle? Phi Z, and how do I get phi Z? It would be whatever, so yeah, I could do tan of or arctan of imaginary over real, right? So but in this case, if I know the power factor is 0.87, I'll say it's inverse cosine of 0.87. And what do I get? I get that it's equal to 29.5414 degrees. Why positive? Why didn't I add the minus sign in this case? It's an inductive loads in the first quadrant, right? So remember the cosine of 29.5414 is the same as the cosine of negative 29.514. All right, so we gotta be careful about that. Questions about that? All right, so what do you think I want to know next? Well, I know I1. I want to figure out I sub A, which is the current in that load. All right, so based my definition up there in the corners, is that current. Okay, so let's do that. And we know from what we figured out, V1 is equal to negative 3,840 volts. Okay, so an SA we just said was 11.494 kVA with an angle of the impedance, which is 29.5414 degrees. All right, that's equal to what? V1, yep, V1 times IA conjugate. Because V1 is the voltage across it. We got that from KVL, basically. So, two equations, right? What are the two equations I have? magnitude and angle, right? So the angle of phi of the angle of SA is the angle of the impedance, right? So that's apparently 29.5414 degrees. What's the angle of V1? 180. And then I subtract the angle of the current, phi IA, and I end up with phi IA being equal to 150.4586 degrees. Okay. Which also tells me that that current is going the opposite direction, which also should make some sense based on the argument that I had laid out before. All right. So in this case, then what else do I need to figure out? I need to figure out the magnitude. What's the magnitude of I sub A? How do I get the magnitude from this relationship? Magnitude of S over the magnitude of V1, right? So with that works out to be 2.9933, like that, amps. So just to do a check for ourselves, this is a lagging, this guy's lagging, right? So if he's lagging, what the heck does that mean? Okay, let's do a check. If he's lagging, what should I check to see if that makes sense? I should draw where the voltage phasor is and where the current phasor is. Where is the voltage phasor? Yeah, it's on the negative real axis here. Here's V1. Why negative real axis? 3,840 is the magnitude, -1, right? -1 always is pointing on the negative real axis. All right, so let's see. And then phi. So IA is here. All right. So IA had an angle of 150 degrees. So it goes, that's 150 degrees right there. Is that lagging? It is, because which one of the vectors is more positive? V1, right? Because remember, going this direction, counterclockwise is the more positive, is more positive. Right? Okay, so this guy is about 30 degrees behind, right? Behind the voltage. Okay. Questions about that?
Supplying voltage.
It's supplying voltage. What do you mean?
In the same way, negative power.
No, it's absorbing power. What you're saying is the voltage across it, if I really drew it properly, the voltage, the plus minus on V1 should have been reversed. And I actually do have a current going into the true plus sign of that. So it is absorbing power. Don't worry your head too much about that. I'm happy to talk with you more about that one. What I was really trying to do was to set up the polarities to be as challenging as they could be in one of these problems. More so than on the test, but this was really more because I really wanted you to be able to make sure you would review this polarity thing on the transformer. That's the kind of thing I will give you on a test to screw with you a little bit, is to mess with the polarities on the transformer to make sure you really know what's going on there. Okay. All right. Okay, so the last thing here now offer to be a little bit tricky. Well, that's a weird looking thing. I want to figure out I sub S. Okay. I sub S, I've said, is the current that is flowing at that point there between the capacitor and load A. How do I figure that out? Yeah, so I would say I sub S would be equal to IA plus I1. If I do that, I'm not sure that I actually wrote that down, but I don't care because I'm not going to look at it too much. That's how I would do it. All right. What I wanted to figure out was say, okay, well, I want to figure out what B sub S is. B sub S being the source right here. Okay. So here's how I'm going to approach that one. Now I said back at the very beginning, this was 0.1 ohms, and this guy was negative J 0.1 right there. Okay. Now let's see what I know. I want to zoom in on that circuit here. So I've been told here's V sub S. I know this current, I sub S, right there. In other words, what I'm going to do is, I'm making Thevenin equivalent here. I'm going to break the circuit right at the terminals in between the capacitor and load A, right? At that point, I have I sub S flowing out, because that's what I've defined over here. This is true if this voltage is what? V1. So negative 3,840 volts. Okay. And I know that this is negative 0.1 J, and this is 0.1. Okay. So how would I approach this if I wanted to figure out V sub S? How would I know how I would approach it. How would you approach it? I'd make Thevenin equivalent. Okay. So what's the Thevenin equivalent looking into these terminals right here? What's the Thevenin equivalent? What's Z Thevenin? God, I asked. Right? So Thevenin equivalent is basically from the perspective of a current that's flowing into those terminals and then splitting between, this is the most important stuff, right? Most important stuff because you get into network one, or sorry, into electronics one, they're not going to ask you P and Q. All right. If you take me again, if you're electrical, you take 3142 with me, you'll have to do that. All right. But that's 2 semesters away. Next semester, you need to know circuits. So prepare, make sure you're ready for that stuff. So Z Thevenin would be 0.1 in parallel with negative J 0.1. Okay. What's V Thevenin? What's V Thevenin? Well, it turns out the number specifically is negative 3840. Right. Well, let me be careful about that. It's not that, right? In the loaded circuit. What's looking at that network? What is V Thevenin? How do I figure out V Thevenin? What is that combination of things there? That voltage source, that resistor, and that capacitor. It's a voltage divider, isn't it? So how would I write the relationship? Vs times negative J 0.1 divided by negative J 0.1 plus 0.1. That's V Thevenin. So what I'm saying is I could take this whole network up here and I could think of it as V Thevenin Z Thevenin and I sub S is right there. And V1 is right here. And if I wanted to, I could draw in the rest of the stuff. This is load A. This is over to the transformer. So this is I1. And here's load B. All right, so I just made a Thevenin equivalent thing here where I basically said, all right, I want to replace all that stuff with this. Okay, so if I want to figure out V sub S, what do I do? Well, from this thing right now, what can I say V Thevenin is? Looking at this circuit, if I just looked at that circuit, what would V Thevenin be by KVL? What's V Thevenin in this circuit? Just by a KVL around this. So it's V1 plus IS times Z Thevenin. Right. Now, if I wanted to figure out what V sub S has to be, I would take what this answer is, right? And I would say this has to be equal to V sub S times negative J 0.1 divided by negative J 0.1 plus 0.1. Like that. And I solve for V sub S. All right. And I'll post that number in my final notes. But anyway, that's the process, right? I did this a little bit too, because if you look at the practice exam, I gave a Thevenin equivalent transformer combination, right? I wanted you'd be thinking about how you could make those combinations. All right, that's it.
Monday.